I appreciate the tail end of the day having people here, so thank you, and thank you to the organizers. So look, my talk is really going to be a bit of a conversation about modeling, specifically on trading models, in fact, which I've spent at least 10, 15 years building in financial markets, and a bit of the learnings from that. So the talk has got three parts to it. The first part is some duplicity in the title. The title was Better Explanations or Better Decisions in Financial Markets, right? Unambiguously, it's better decisions. In finance, irrespective of what people tell you in the fluffy documentation, it's really about the profitability of your strategies, and you live and die by that. So it's better decisions. This is just the fact of life. There's a tendency in industry to want explanations, and what I'm going to try and convince you is that in financial markets, at least within, say, under 1 day, a frequency under 1 day, there are no real explanations. I mean, there's nothing actually in the box, specifically for liquidly traded assets. And this is worth thinking very, very carefully about, because there are some hidden assumptions in the machines we build and the models we use. And perhaps at the end of the talk, I hope that you'll think more carefully about maximum likelihood, about whether or not maximizing any utility function or any objective function is actually a smart thing to do, when that is actually what is driving the system. So just to start things, this is from Alice in Wonderland, and that's the Red Queen. There's the Red Queen hypothesis, which is in any complex adaptive system, the faster you adapt, the faster you have to run to survive. And if there's one takeaway, that's what financial markets are. Specifically under, let's say, 30 minutes, this is a pure arms race. There's nothing in the box. This is just one algorithm against the other algorithm, modulated on information available. So this is how I would prefer you to think about financial markets. Is on the left, it's LHC. On the right, that's the New York Stock Exchange. And then some fine print over there, which we can talk to. And think about financial markets as a social science collider. So financial markets, specifically high-frequency markets, are, as I said over here, to finance what particle accelerators do to physics, with one big difference. In physics, there's actually nature. There's actually something real and tangible out there. In financial markets, it's just your competitors' models. Whether it's a qualitative model in your head or one on your box, it's the same thing. This is just pure competition between models. But what we do know is the faster you adapt and the more data you store, the further behind your competitors you are. And I'll just read the fine print here. So this is from the Cisco Global IP Traffic Trends Report. This is from March this year. And currently, 1 to 2 exabytes of financial market data is transacted on per day. By 2020, it's going to be 5 to 10 exabytes per day. And 99% of the data is completely worthless by the end of the day. That's the frightening thing. So the fine print here is you think that you have lots of data, but you don't. The other point is that the whole thing's hierarchical. And so we call this top-down and bottom-up causation. And the way to think about it is, if you're a trader, I'm not talking about day traders, right? Because day trading is really how do you game people to spend money? I'm talking about real trading. I mean, your prop trader in a bank, or your high-frequency trader, right? What they are doing is gaming the rules. It's that simple. They are given a box by the regulator. The regulator defines the rules of the game, and their job is one thing: game those rules and basically decimate your opposition. It's adversarial. So inside the box that has been kindly given to you by the regulator, it's game on. And it's worth thinking very, very carefully about. And this is this whole notion of top-down causation, is that there's this misguided belief in the trading, let's say the external view of the trading world, that it's bottom-up. It's somehow lots of agents with sort of supply and demand, and there's some equilibrium, and there's information that you're using, and it somehow aggregates up to the price of assets, and then the price of assets aggregates up to asset classes and so on, right? That's not how it works. It is really top-down. Give me the rules of your exchange, give me the tax rules, give me the regulatory environment, and we'll build machines that will game that. So it's regulatory arbitrage. And that's when we talk about it in terms of hierarchical causality or top-down, bottom-up causation. The other interesting thing is the wider the data is, the more we have to store, and then the faster our competitors adapt to us. So you're almost always behind the curve. So these are 3 points to think a little bit about. Some papers. I'll advertise this paper of ours called Hierarchical Causality in Financial Economics. It's kind of light, but it'll give you some of the sense of why we should care and think a lot about these hierarchical systems. The other thing I want to try and sell is statistical sciences, specifically to the younger generation, is that I think over the last 20 or 30 years, there's been a misunderstanding of what statistics really is. And so I'd prefer to rebrand it as data-intensive science, the logic of science, if you'd like. So statistical science is driven by data, and it's not only data fitted to thoughtful models. So historically, a lot of statistics has been about fitting data to thoughtful models, models that we come up in our own minds. But I think model-free statistics, which call it algorithmic science, is pretty much becoming the standard, that you need both. And I see very little difference between them. Whether you come up with a model in your mind or a machine comes up with a model for you, it's just a model. There's actually a layer of logic below it which you should think more carefully about. I'd recommend a book. This is a classic by the statistician E.T. Jaynes. If anybody knows anything about probability theory, they'll recognize the name. And he wrote a treatise called The Logic of Science. And it's well worth visiting. It is very Bayesian in nature, but there's a lot of kind of gems in there, which I think a lot of people in the machine learning community could take credence of. It's why thoughtful models and statistical learning are a bigger game than machine learning. And so this whole argument of a right to an explanation versus the right to better decision, I mean, I would submit that machine learning is about better data-informed decision-making, point blank. That's machine learning. In the bigger scheme of things, let's call it statistical sciences, they are concerned with estimating models, calibrating models, machine learning as well in this sense, but also statistical learning in the sense of generating equivalence classes of model representations. And I think that's where the real action is happening now, is finding equivalence classes of model representations. One way of thinking about that is just a heads up for later in the talk, is when you maximize a likelihood function, you're actually maximizing something called Fisher information, and Fisher information is actually a metric. So it gives you the distances between distributions in the space of all distributions. And there's a lot of really interesting work happening now trying to understand the geometry of these kinds of model representations. And it has a very deep link to learning machinery called energy-based learning, so restricted Boltzmann machines, Potts models, which I'll talk about, all these energy-based models which are pivot on Gibbs-Boltzmann distributions. They fit very, very neatly into this whole theory of the geometry of distributions. So something else to think about. That machine learning is looking as though it's a very small subset in a much bigger, much longer game. And that longer game can be seen if you go and read what these guys are doing in the 70s and 80s in Bayesian theory. Okay, so in terms of the ethics of it, which I won't go into too much, I think the next speaker will kill that for me. In finance, I think this is an irrelevance. And I'll try to explain to you why. It's who cares about the target function? Who cares about the best model or the best explanation? If it's making money for your shareholders, not your stakeholders, your shareholders, it's working. And it's not nice. The world's not a nice place, but that is the society that we've crafted. And yes, we should interrogate whether that's a society we want to be part of, but that is the society we're part of currently. So let's not mince our words on that. But can we ever have both? I mean, truly, can we ever really have good explanations and good decisions? I doubt it. And just have a look at a history of mathematics. So this is a bit of a long-winded thing, which I'll read it out for you. Will the positivist dream of statistical sciences go the same way as the normative Hilbert program of mathematics? So the Hilbert program of mathematics was that we could just write down axioms, crank some handle with the axioms, and generate all the mathematics. So mathematics is just a computational problem. There's no discovery, or there's no kind of some spark of insight in the human mind that generates new mathematics. It's just axioms, crank the axioms, get all the mathematics. And that was pretty much killed by Gödel and Toski. And it's worth thinking very carefully about, because if you look at what's going on in the world around us, we seem to be making the exact same mistake. But on the other side, like the pendulum swung the whole way through, and now we just need data. Data will tell us everything. Okay. It may work in the natural sciences, in physics, in cosmology, astronomy, whatever, right? But I do not think it will work in finance, because there may not be anything inside the box. I don't think there's anything inside the box. So should we care about the difference? Yes, we should, but the way currently financial markets work, it's an irrelevance. Can we ever really have enough data? No, not in financial markets, not in trading horizons. Can science ever become purely data-informed positivist? I doubt it. And not until I doubt it until we understand the difference between generalized artificial intelligence and artificial intelligence. We're all generalized artificial intelligence. We are much, much more than just some deep learning network. It's not to say that we won't get there, but not until we solve that problem, I think, can we rely just on some data-informed process to do science. In finance, it's different because it's a social construct. Hidden in this GIA-AI debate is really, is there a difference between innovation and invention? So a show of hands, how many people think they're the same thing? Right, and why? Exactly. So, and it's an interesting thing, right? And you're not the only one. From the business world, it's not about invention, it's about innovation. The business world is about taking different pieces of technology, putting them together to add value to your clients. And so it's really incremental. So there's interesting work done by INET, which is a complexity research group in Oxford, and they've shown that just by combinatorial arguments alone, you can explain the growth of patents in the US. All right? So it's just combining previous incremental improvements that should generate the growth of patents. And that's innovation. And that's something that business is focused on. Business is not focused on invention. Invention is coming up with new mathematics, coming up with some really radical insights into how the world works around you that you cannot derive from the axioms of the system. I'm loath to say paradigm shift, but yes?
The question isn't the same as saying that all invention is discovery.
Most.
It's making a distinction between mathematical, like some synthesis of knowledge.
So in innovation, a lot of technology is just innovation. But underlying innovation are true kind of shifts in the way people think and do things. I mean, deep learning is, I think, a lot more than just innovation. I mean, the way the optimization problems have been solved, I would submit that that's right there in the invention game. You know, it's been around for a long time. Yes?
But then how do we go about defining what is innovation?
And that's the tough question. I don't have an answer for that. But with hindsight, it becomes pretty obvious. I mean, using the grandiose views. At the time when, I don't know, Einstein finally figured out general relativity, right? And after his 2 years of not believing his own math, in hindsight, 100 years later, it looked like a radical change in how we view the world. At the time, I think it was very, very difficult, given all the other competing theories. So with historical hindsight, it's very easy to see where innovation and invention kind of are separated. But I don't think we understand science well enough to say, this is how to do it. That's just my feeling. I mean, there are people here who have far deeper knowledge of philosophy of science than I do, like Professor Bassett and so on, right? I mean, anyway, so can we ever disentangle languages or culture from science? I mean, that's the Toski problem, not a chance. And that's a huge problem. In the business model of science, I mean, how do luck, skill, and influence networks shape the world? If you actually look at what the world is, the social construct. And financial markets are a microcosm of it, a very extreme example of it, which is why I think doing research in high-frequency finance or trading is so interesting, because it's a very, very clean snapshot of basically luck, skill, and influence networks gaming each other. And I don't think we spend enough time thinking about this problem, is that, so much of the world around us is shaped by these influence networks and a lot of luck. How much skill actually shapes the world? Actually, a very little amount of skill. There's some very nice recent work showing that in the publication cycles, most cited papers, highly cited papers, are cited because other people cite them, not because they're actually making a contribution. It's something to think carefully about. And at the heart of all this is, why do we use randomness? Why is ideas of stochasticity so fundamental in science? And the main reason why stochastic models, in my mind, are useful is they hide infinite degrees of freedom. Is that all of science, as we know it, you need a very, very small subset of parameters that you can fit to the data. So you need to hide effectively an infinite degrees of freedom somewhere. And the only game in town is to hide them in some random process. And that's quite depressing. On the deep learning side, just to get a sense for this, there's a really nice paper by Mehta and Schwab on arXiv. It was 2014, which showed that there's an equivalence between this renormalization group method, which I'll talk about briefly, and deep learning, right? So I'm interested, my research area is really spin models for learning, spin models for clustering. The reason I'm interested in them is because these spin models are a way of unifying maximum likelihood methods, unifying a lot of machine learning methods and stuff. And this is just to try and provide you a bit of evidence, you can go read it, to convince you that deep learning networks are just a very, very special case of spin models. And spin models themselves come out for another class of models, which come out of this geometry of distributions. And the idea is that it's a renormalization group. Is the idea that you have a whole lot of spins, which is like a pencil with a spring tied together on a table, let's say, and the pencil is either up or down. So up, pointing up 1, down 0. And if you have this whole floor covered with all these little pencils stuck together with springs, and you push one pencil down here, you can force a cascade where suddenly all the pencils are now 0 on the floor. But what if there's some random process flipping all these pencils up and down? Then you get some interesting dynamics. So what renormalization group argues is that if I take little groups of pencils, say 4 at a time, say 4 little pencils, and I average that into some one new pencil at the next layer, and then I take 4 of those little pencils with in a little group, and I average those to a new layer, and you keep on doing that, you recover exactly the same maths that you have for deep learning networks. It's just basically layers of connected nodes. And you can make that as complicated as you like. So it's just a name, but the classic model in physics is called the Ising model, which has just on and off, so it's a classifier problem. But there's a much more general class of problems called Potts models, where the spin number can be a real number. And then you can do some really interesting math with that. So at the end of the day, I would like you to think about these questions, and I'll argue we never have enough data. But what are we actually doing? So there's nature out there. In the natural sciences, there's some real world we can do experiments with, and that real world doesn't change over the time scales we've observed it in the sense of energy conservation and momentum conservation. So let's say there's some inputs X and some outputs Y, and we'd like to predict these outputs from the inputs. And let's assume that there's actually something inside the box. So what we do is we try and build a model. And we hope that the model that we've structured over here somehow replicates in a faithful way what's going on inside the box. And so what we've done for the last 300 years is we'd estimate a model or calibrate a model, and these are not the same. So estimate is very normative. So in economics, you estimate models. The reason is that you have a very good explanation, consensus explanation for why these variables should be important, and then you go off and you estimate how important they are in your data set. But it's normative. Well, in a calibration problem, which is like option pricing, You know the model's wrong. You know Black-Scholes-Merton is wrong, but there's some fudges that allow you to make it work on real data. So you have an applied volatility. You go measure actual option prices, and you go and fudge the implied volatility. So it's a calibration problem. You know you've got the wrong model, but you're going to basically smash the model onto the data. So it's worth thinking about this difference, right? Estimation versus calibration. And typically the idea is to validate a model. Is you want to find data that you didn't use when you either calibrated or estimated and see how well it generalizes out of sample. But you're actually looking for both information, some insight into what's going on inside this box we call nature, and you want to make predictions, make good decisions. And I'm going to call this the territory, and I'll explain to you why. Now, in a model-free world where you're not trying to pick the model, you're trying to let the data pick the model for you, there's an approximation that you're trying to estimate over some class of target functions. There's a whole bunch of functional forms out there or distributions out there, and you just want to sort of use the universal approximation theorem and fit these, right? And then you'll use the same idea as before. You'll do some validation process, and it's purely based on predictive power. And it's decision making. And I'm going to argue that in finance, there is no difference between these, because when you have liquidly traded assets and huge amounts of data with huge amounts of agents, there's nothing inside the box. There's just responses between the agents. But what is really interesting is for this territory, there's actually a map. Now, in science, the way we think about it is we actually think that there's a territory, and somehow we're going to go and explore the territory and draw this map. And the map will never be as good as the actual territory. You're going to go wander around Rondebosch with a piece of paper and decide where all the buildings are and all the trees are and all these interesting things. But it's never going to be the case that you draw the map and then the territory appears. But in finance, it's the other way around. So the map we're actually using, and this is in all of science, is that we actually believe that there's some objective function that we can maximize. There's some, let's call these variables S, so those are known variables, and the variables T are unknown variables. And we're going to measure some data from nature under the assumption that there's some objective function we're maximizing. So we're going to find some optimal set of parameters. And this set of parameters is a mixture of parameters we can know and those we can't know. Right, so S, known parameters, that's relatively plausible because as a generalized artificial intelligence, we can go out and measure stuff. There should be some unknown parameters. That's also relatively plausible. But is there actually a single unique objective function? Big question. And there's no answer. Everything we build in statistics and science assumes there is something we can optimize. It's not a given. That's quite interesting. The other thing is that there is some optimal choice, some unique, singular, optimal choice of parameters. How do we know that? We don't. Then we assume that you only need to optimize over the known parameters, S. So we've pretty much reduced the space of objective functions to those where we can average out all the unknown parameters. That's quite specific. All right? And then at the last step, we want to find a probability that what we predict actually matches nature. This is actually a very, very special situation. And it's starting to puzzle a lot of people in statistical learning. Because is it by the whole construct of maximum likelihood that the world around us looks the way it does? Or is it telling us something real or true or faithful about the world? We actually don't know. And in finance, it looks as though that's the game we're playing, because there's nothing actually in the box. That's the problem. Some papers, if you're interested. The terminology map and territory comes from this work by Eric Houle, and he asks the question when the map is better than the territory. Another way of phrasing this is that when does top-down causation dominate over bottom-up causation? There's also work by Matteo Marsilli and his collaborators, Mr. Matteo and Rudy. And there's a classic paper I urge everyone to look at by Leo Bremen, which I'll talk a bit about on the next slide. And it really got to do with why does science work anyway. And in finance, we're in a unique situation where we can actually explore this question because we know it's a social construct. We have evidence that it's a social construct. In the hard sciences, it's very difficult to unravel these. So this is the classic Wigner quote, the unreasonable effectiveness of mathematics, and it's very surprising that we can reduce phenomena to a very small set of conditions. And there's a very specific reason why we can do that. And it's because of this map. What Leo Bremen has argued, was that data modeling, the world of data modeling versus the generative model you have in your hand versus the world of algorithmic modeling where we just fit in target functions, they're not that different. And I'm of that camp. They're not that different. There aren't two cultures. So are they really that different? And I'll leave that to the audience to read. But what is worth thinking about is this work by these guys, Marceli, Mr. Mateo, and Rudy. And the statement is really provocative. Models are predictable only when the number of variables is below a critical threshold. And under very general conditions, observable part of the objective function will take on this Gibbs form or legit form if dependence on unknown variables is not irregular. And it turns out that every model we build in science satisfies this condition. Because those are the only ones we can fit to data with the current technology. That is why this works. The small number of conditions pops out by construction, because those are the only things that we can maximize over an objective function. So I mean, if you want to get some of the literature on that, those guys. More on how the work here ties into that. So we're worried about energy-based learning methods, so methods that use the Gibbs-Boltzmann form. And this includes deep learning networks, POTS models, all the Boltzmann models, all the Boltzmann distribution-based models. And once again, I'd advertise to students to have a look at this really nice paper that links these spin models to deep learning networks to understand how the trick is in practice very clever, but in reality it's not such a clever trick because we've actually restricted the space of models more extremely than we think. So the pet example I've worked on, Checktime, is doing real-time or near real-time cluster estimation for trading algorithms. So what we were doing is we're taking thousands of features from the order book, use very fast clustering algorithms to cluster those features to do dimensional reduction, use that to construct a reduced state space, then we use reinforcement learning on that state space to train algorithms to beat other algorithms. The papers are out there. You're welcome to have a look-see. But, and that led to sort of let's call it a hesitant interest in these POTS models. Because, sure, we can estimate these correlations. Over here, we were doing, this is for 40 stocks, but remember, each stock has thousands of features in the order book, right? So it's probably about 40,000, yeah, but 40,000 features. And then we were doing cluster detection to actually reduce this down to 4 or 5 states so that we can put the 4 or 5 states into an RL algorithm. And so these are clusters in time. So my colleague Stuart, who had a talk earlier today, was saying that, you know, this is contested space. Not everyone thinks that you should be clustering times, but it does seem to work quite well. Anyway, so this is it's an example of two things, a phase transition and a clustering algorithm. So the kind of clustering algorithms that we're interested in things called super parametric clustering. And if you can see the slide up here, I'm sorry that the quality is not so great, but this is temperature, so basically the variation in the noise in the system. This is on the right magnetization, which is this curve over here, which is essentially in that little model with the pencils up or down. Magnetization is average over all the ones and zeros. So if all the pencils are up, it averages to 1. If lots of pencils are up and down and flipping the whole time, it'll average to 0. And so this is very physicsy, right? So I mean, I come from the statistical physics domain. So we'll talk about when the world is very warm, very hot, it's very random, and your magnetization is very low. And when the world is very ordered, magnetization is very high. And so you'll have some ferromagnetic phase and some paramagnetic phase. And in between there, near the phase transition, it's called superparametric. And this other variable, susceptibility, which spikes, for our statistics colleagues, you should think about the Fisher information. That is the Fisher information. So why these classes of models are interesting to us is because it gives us insight into the broader class of models where you maximize Fisher information. So the Jeffreys prior, I think one of our former colleagues mentioned, it's pretty much trying to investigate how those kinds of systems work. And just to give you a sense, so this red line is at a high temperature, and then we jump through the phase transition, and the whole thing coagulates into a single cluster. And what is really interesting about these kinds of models is that there's no dendrogram. You can show that there's no dendrogram. You have a configuration, and over a very short period of time, you have a completely new configuration, and it jumps. So these classes of models are interesting for trading because you don't need validation. The maximum likelihood method solves for the number of clusters and the configurations concurrently. That's why they're quite useful for trading. But for the science we're trying to do is really want to understand these phase transitions, how real-world systems go through these phase transitions. And this is for S&P 500 data. This is a 90-day trailing window. And these are actually these are stock clusters. And as we go through different temperatures, we get different kinds of correlations. The only thing I want you to take away from this is that there's a deep link between spin models and maximum likelihood methods. There's a deep link between spin models and maximizing Fisher information. And Fisher information gives you a geometry of the space of distributions. And understanding that geometry in the space of distributions and how restrictive our methods actually currently are, I think is worth thinking about. On a more kind of, so that's that comment, that the only real trick we know is finding parameters near the maximum of Fisher information. So sometimes the Fisher information will explode, but we're always finding those parameters near to the maximum Fisher information. And it seems that those are the only models that we can actually infer from data. And they're a measure zero set. So in the space of all possible models, the only models we can infer from data are in this tiny little space when we can actually do this. Everything in science is built on that. In finance, why we worry about this map territory game is that we've done some research into agent-based models where we generate different kinds of agent-based models and try and calibrate the agent-based models to trading data. And what we find is that it doesn't matter what agent-based model we build, how complex, the parameters linked to the behaviors of the agents are completely degenerate. And the parameters linked to the structure of the market, the box the agents are in, completely define everything. So we know in the trading world, at least under 1 day, the box determines all the possible behaviors that agents can engage in, and the agents go forth and they engage in those behaviors competitively. So it's completely top-down intraday. So in the trading world, the map defines the territory. Okay, so just to wrap up, my last few comments again is that the system seems to adapt faster than we can store data. So you never have enough data. The system has both top-down and bottom-up causality. And that means that the game the regulator plays determines how the agents will compete. So the regulator is actually the source of profit in most modern financial markets. It doesn't matter what they do. Everyone's just gaming their rules. That is the game. And it's quite depressing when you think that regulators are the business model. All right. So models are the camera in the natural sciences, and models are, let's call it the engine in finance. For those who want to read a bit more about examples, there's a really nice book by Donald McKenzie, published in 2006, called An Engine, Not a Camera. This is where I get the terminology from, how models shape markets. Okay, and then even more kind of controversial in finance is that, yeah, you can't go back to yesterday because the world was very different then. So you never have enough data. Okay, thank you. That was interesting. Yes. comes up, all right? What question about Bitcoin? So the regulator is there to protect the interests of the uninformed investor. And unfortunately, Bitcoin, worded carefully, no, won't. It's a Ponzi scheme. Let's be honest about it, right? And I think a lot of people made a lot of money out of it, and good for them. But they learned the rules of the game, and they played it very, very cleverly. And I respect that. But it's not anything new. I mean, go Google tally sticks. I mean, there's some really interesting stuff that was going on 500, 600 years ago that is no different from Bitcoins. It's just another Ponzi scheme. Yeah. Sorry, anything else?
I sort of want to go back to what you said way earlier, which if it's making money, that's the most important thing. And then I want to bring that back to choosing the correct models and optimizing those models. But isn't it, if the model's working, then it is the best model?
Yeah. So, this is this whole problem of backtesting in-sample and out-of-sample versus how you measure your errors in your backtests and blah-de-blah. At the end of the day, most trading strategies, even in backtests, cleverly crafted backtests, where you're actually testing with information you never had, you can't monetize it because you don't have a business model. And I'll give you an example. So I can go off and build a trading strategy, and let's say I earn 1% a day. Before costs, and then I go and figure out, okay, so I'm going to lose, 45 to 50 basis points on transaction costs today, and I don't know, let's say there's settlement fees and a whole bunch of other levies for another 25 basis points, left with 5 basis points a day, right? What they don't tell you is that there's still STT in South Africa, so there's another 25 basis points. There's still all the business costs associated with setting up the business itself. So there's a whole bunch of costs which are very, very difficult to put in any backtest. So currently where we are now is that the only way to really test your trading strategy is go off and trade it, and after a year, did you make money? Could you pay yourself a bonus? I mean, it sounds really kind of brutal, but so if you've got something that works, yeah, think very carefully about the generalization error. Go and do your Hoofding bounds and your VC dimension for your algorithm. Go do lots of scenarios and stuff like that to do risk management. But if after a year you've made some cash, you've done extremely well. And I think that's difficult for these businesses because so I separate trading from investing. These are very different games. In investing, the explanation does start to matter because you have certain liquidity issues. So when I said profitability is everything, I'm being provocative, and I do believe that is the only measure of success for any game in finance. And for me, that is why finance is so interesting, is it is actually one measure of success, unambiguous. It's not how good your predictions are, it's did you make cash? It's really clean, all right, in that box. But if you have an illiquid asset, like private equity or some asset that's never traded before, you're not going to have data to make any inference. And then things become quite foggy. So when you have liquidly traded assets with large amounts of data, yes, it doesn't matter. You don't need an explanation. There's nothing under the hood. You just trade in information relative to your peers. But if you have an illiquid asset that has never been seen before, that you can't link to anything else, you can't hedge it with anything else, then all bets are off. And then that's this whole phase transition regime change story. And I think in investments, it's quite a subtle thing because somehow clients seem to think that there's an explanation for everything, but there isn't. And there's always this debate, fundamental